So this is if f of x is continuous. If f of x is continuous. And I want to show you guys a couple examples of like how they look on the graph, like which ones are continuous, which ones are not continuous, and the ones that are discontinuous. What do they look like, and what are the different cases?
Would it be like
All right, so let's take a look at this first one. There's different types of discontinuity. All right, we have the two different types are shown right here in this one, and these guys right here. Okay, this first one right here, this is a removable discontinuity. And the reason why it's called removable is because the limit does exist here, except it's not the same as when you would plug it in. Okay, let's say, for example, this is f of x. Whoops, that was supposed to be an arrow, and this is f of x. Okay, if I were to find the limit of f of x as x approaches 2, you can say that that limit equals what?
5.
Now look at the graph. The graph, as I come from the right-hand side, approaches 5, right? And if I come from the the left-hand side, it approaches 5 also. And so your answer here is 5. Now this graph is discontinuous, which means to you that you cannot just substitute it in to find it. Now here we have a picture, a graph, a visual. We can look at it and tell. But what if it wasn't a picture? What if it gave us an actual rule? If it gave us an actual rule, that means we can't just plug in 2. We can't plug in 2. We can't just say, oh, the answer is going to be when you plug 2 into f. Because if I plug 2 into f, what is that going to give me?
No, it's going to give me under.
It's going to give you 10, right? If I plug in 2, I'm going to get that point, which is 10. Okay, so here the substitution doesn't work because it's not continuous. Okay, now let's look at the bottom ones. The bottom ones is our other situation when it's not continuous. Now, this one's called a removable discontinuity. These bottom ones, they're called jump discontinuities. And they're called jumps because of the big gaps that they have. Okay, and let's talk about those a little bit more. Okay, look at this guy on the left. This guy has absolutely no limit if you just, like, say approaching. Well, actually, they all don't just have a limit. You have to have, like, you have to follow a special rule, like coming from the left or coming from the right to find the limits. And then we have this dot just chilling right there. What does that mean? Okay, well, you see these ones right here, how the dot is attached to one of the parts of the function? Well, these ones are special because they have, they're like this one's right continuous and this one's left continuous. And they're called continuous there because they have a closed dot at the end of it. What does that mean? That just means that if you were finding the limit for this one right here, if you're finding a limit as x approaches 2 of this function, we'll call him f of x, we can plug this in. We can substitute it into the right side of the graph. So if this was a piecewise function, you could plug in the 2 into the right side of the graph because it's right continuous. Well, I think this is still confusing. If you're looking at this for the first time, it's still confusing to me. So let's look at an example. Let's look at a piecewise function. We'll come back to that. So here's a piecewise function. Let's graph this guy really fast, and then we'll be able to talk about him some more to find the different limits that we can do with this. Now this one's not continuous because there is a jump in it. But let's see what it looks like first before we start making accusations. Okay. Now, this is a reminder for a piecewise function. If we wanted to graph this part right here, here's our rule, and this is kind of like the domain for that rule. Okay, this says that for every x that's less than 1, you plug it into this part right here. You don't plug it into these ones. You just ignore them. Okay, so for less than 1. So here's one right here. You guys know what x looks like. And just whatever you plug in, that's what your y value is. And so if I plug in 0, I'm going to get 0. If I plug in negative 1, I get negative 1. If I plug in negative 2, I get negative 2. If I plug in negative 3, I get negative 3. Okay, so that's negative 2, negative 1. So this is my graph so far. Okay, now I get closer and closer to this guy right here, but I had to put an open circle there. You guys know why I had to put an open circle there at 1?
Less than 1. It's a rule.
Yeah, because this says we don't plug in a 1 to it. So you have to put an open circle there. As soon as you get to 1, you're supposed to plug it into the next rule. And the next rule is 3. There he is. If once I get to 1, I plug it into 3. And so I go up to 1, 2, 3. And I put a dot right there. Because if I plug in 1, I get 3. If I plug in 2, I'm also going to get 3. And if I plug in 3, I'm also going to get 3. If I plug in any numbers in between, I'm going to get 3. So in this interval, our line is right there. So now our function made a little jump there. That's why we're not continuous. Okay, now after we get past 3, we go to 4. We're back to this other function. And so when we plug in 4, we're going to get 4. So we go back up here, put a dot there, and then we plug in 5, we're going to get that. We plug in 6, we're going to get that. And so our graph looks like that. Now, what about this part right here? What if I plug in 3.5? What's that going to give me?
3.5.
That's going to give me 3.5. So technically, I should be connecting this to this right here. But do I put an open circle or closed circle there?
Open.
Yeah, for this part of the graph, I would put an open circle there. But there's already a solid circle there. So is it continuous at this point? At x equals 3, is this graph continuous? And the answer is yes, it is continuous. You see how the line's connected? If I were to draw this part of the line right here, I do not have to lift my pencil. So therefore, it is continuous. Okay, if I look at the function as a whole, it is discontinuous. It has a jump discontinuity. So we have our function f of x. Is there a limit of f of x as x approaches 1? No, there's not.
One side.
Why? Because this side approaches 1 and this side approaches 3. There, this is the approaching part. I'm approaching, and it's approaching 1. I'm approaching, and it's approaching 3. Okay, so there is no limit there. Is there a limit coming from the left-hand side? Yeah, so if I change this to from the left-hand side, there is a limit, and that limit is, what's that limit? It's 1, right there. If I come from the positive side, it's not going to be 1, it's going to equal 3. Okay, now, what we were talking about earlier, the continuous, this function is continuous coming from the right. And because it's continuous coming from the right, that means if we wanted to find the limit coming from the right, we can just plug in 1 to our function to get our limit value.